All right, so we're gonna talk about modern physics. To do so, I have to give you some perspective as to what's going on before that. So it becomes a history lesson of sorts. But also part of the science is to say, look, you have to realize that how do we know what we know largely depends on, you know, what experiments led us to these conclusions. So it's not sufficient to simply say you can't go fast at the speed of light because although we know that and we think that's pretty darn close to true, how do we know that? Why is that sufficient? What experiment shows us these things? And so let's talk briefly about where we were. You should know, hopefully, that Sir Isaac Newton created classical mechanics. Classical mechanics were very well understood by the middle 1700s. There are some things they still had to work out, but for the most part, classical mechanics was almost done. In addition to that, somewhere about 1700, 1770, 1780s, circa Ben Franklin, they started to work on E&M. E&M, electricity and magnetism. What is this and how is this working? And so they started working on it. About 1860s, a guy named Maxwell sat down and created the laws which you were using. Now, granted, Faraday is the one that came up with the laws you actually use because Maxwell's laws were mathematically ugly. But he had connected classical mechanics to E&M in a way that was way beyond simply, well, this is really interesting how this works. He was basically going to land of, I can explain the universe. My equations, when put together with a bow on top, with all the strange calculus you have to throw in there, could explain anything you've ever seen in your life. And he was convinced, or at least people around him were convinced, that he had basically solved the universe, that physics was done. It had a package and a bow on it. It was so much so that a guy named, I'm going to look down here, a guy named Duell, who was in charge of the patent office in 1902 or 1901, said, hey, God, it's so disappointing. Like, I've seen all the science, experiments coming in now. There's a huge rush because this beautiful physics has gotten done. People invented things like phones and all sorts of things. The experiments coming in are pretty much dead. And we're done. I mean, there's nothing new as great as ever going to happen again. We've gone past the point where new things and incredible inventions are going to happen. Okay? So that's where we're at. It's so much so that a guy named Albert Einstein, working as a Swiss patent clerk, mentions, by the way, that he thought there was some chance the patent office should be shut down. That's ironic, considering what he ends up doing with the rest of his life. He spends some time looking at the little dust motes. You know, sitting there, if you're sitting in the light in a lazy summer day, you can see those little flecks of stuff floating in the air and bouncing around. That's because the air molecules are hitting them. Albert Einstein proved that was so, and proved that you could actually model how these things move around, and as such got a Nobel Prize, because really, it's as good a physics as you're going to get these days. That's it. That's all you're going to get. Don't get too excited. That's the limit going forward. Now, good news is we are modern scientists, which means we are still going to experiment to prove whatever we know to be true. There were some experiments. They're often called the 5 great experiments. Honestly, there's a lot of them. 5 is kind of a funky number, but we'll go ahead and do the 5 great experiments. And then you might count them and go, Mr. President, there's more than 5 here. Yeah, there might be more than 5. So, what are the 5 great experiments? What to do with something called black body radiation. Black body radiation is fascinating because you should know in the universe has heat. Even cold things have heat. What do you mean by that? I mean, everything has to have heat. In order for electrons to whiz around your atoms inside, okay, in order for electrons to whiz around the outside of your body, they have to have kinetic energy. Kinetic energy is heat, so therefore everything in the universe has heat. The molecules are banging together, everything's happening, everything's shaking. Everything's got heat, unless it's absolute zero, which we can't reach and nothing can reach. So therefore, everything has heat. If everything has heat, it has to glow. It's to put out light. Okay? So that's why when you go to one of these nice museums of science industry, you go running through the place, you can see an outline of yourself in front of an infrared camera because you are glowing heat. Okay? You are shining light. Now, why was black body radiation something that couldn't be explained? Well, because one of the things that was fascinating about this was we knew that each photon of light had a certain amount of energy associated with it. That certain amount of energy associated with it was really, really small, which meant that me glowing here, I should be able to glow in any color I want. I should be able to glow gamma rays and fry you. Not many gamma rays because it's a lot of energy, but if I'm glowing, why do I just glow infrared? Why am I just basically warmth, a little bit of color, nothing much exciting happening? Why is it that I don't fry people? No reason why I shouldn't. And physicists were disturbed by this because they couldn't figure out why you can't fry people. The second thing was this. They discovered by carefully looking at people, they only glowed at certain frequencies. They'd take a black object, they'd heat it up, they'd sit there and stare at it, and they'd notice no matter how hot they made it, it glowed the same frequencies. That made no sense. Why would it pick certain frequencies? Why not anything? Anything is possible. So it was a kind of a strange, like there's no reason for this. But again, somebody will figure this out. It's not really a reason to change all the physics we know because physics works, right? Why do I mess with all this stuff? So the next thing was Planck. Planck's similar idea. He recognized that if you have an atom, and we're just going to do hydrogen simply because it's easier to deal with, you have electrons whizzing around. These electrons are whizzing around, and he was excited about electrons. I'm talking about electrons. You should only have one because it's hydrogen. I drew two, but you know where the shells are. I guess there's only one. Okay, so you're sitting there looking at this picture, and you go, okay, fine. So what he realized is there's something called electromagnetic spectrum. It glows certain specific frequencies. Seems a little strange. It gets worse. Planck discovered that if an electron goes from one place to another place, it's going to lose energy, potential energy, right? So therefore, we know you did energy. You can calculate. You can even use all the little physics we know. Remember, we've got potentially over r squared when we're talking about over r. When you're talking about planets going around something, if you change your orbit, you come to lose some of that energy. That energy was light, and so he recognized fairly early on that the way it was conserving energy was by making light. What made no sense at all is why are there only a couple colors? Why isn't it infinite, right? Because if I go from, say, this shell to this shell, that would be one color. From this shell to this shell here, it would be a different color. In fact, if you imagine an infinite number of different things, you could get an infinite number of colors. Why were there only specific colors? So Max Planck started to get very fascinated about the fact that there didn't seem to be lots of different, there should be a couple, which meant that there was only a couple ways in which electrons were going from one orbit to another orbit. And that was really strange. And so he was starting to scratch his head going, how is this possible? Further disturbing to him as he started to think about this problem was the photon of light. Now, Albert Einstein talks about photons early on in the early 1900s at the time. So we're talking about some things simultaneously happening. Basically, they emit one photon of light, which means they lose all their energy instantaneously. They go from here to here, they travel in between. Because if they point, they would have to put out two photons, one to get to the halfway point and one there. Even that instantaneous steps, wouldn't it? Of energy, which is how this energy is stored, right? When the color be like a rainbow as it fell in, right? It would lose a little bit, different colors it started to fall in. Instead, it emits one photon of the specific color you're talking about, rid of all the energy going from here to here, and instantaneously the electron has to travel from one place to another place. At least that's the way the physics worked. Ain't like that at all. Electrons shouldn't be teleporting around, and electrons shouldn't be stuck in specific shells. Yet, as Max Planck was working, he discovered something fascinating. That his work suggested you could only have two electrons on the inner shell. And we know the chemists have been doing that for approximately 300 years. And they couldn't explain why, but it matched that expectation. It matched the fact that they thought it must be the same thing. And he discovered that you had to have 8 electrons on this shell. And by the way, 6 of these electrons are acting to have different energy levels than the remaining 2. Hence your P and S shells. He studied stuff in chemistry. His observations started solving chemistry problems. But they led to a physics problem that's ridiculous. Why does an electron, like, it would be like, and here's a planet that's going around the sun. It'd be like saying, hey, a planet can be in this orbit or this orbit, but never in between. Oh, and by the way, if the planet wants to go to here, it would emit a tremendously teleport between the two. Max Planck didn't make sense. And that's reasonable. It should make sense. The problem was, how big are electrons? Really, really small. He's got no way to determine directly what's behind the electrons with his electron, look at them through binoculars device. He has no way to do. So this is called, this first one is called the black body radiation. Again, why is it only emitting certain frequencies? Second one, and this is the more important of the two, Bohr's observation that you can only have certain orbits around an atom. And it must be the electrons are teleporting from one spot to another spot and somehow losing the energy instantaneously between. These two ideas together create a huge problem in terms of what you're thinking. Now, there's one other thing that comes along with this set, and let's do that one now. File new. If I can get this to go, file new. Save. All right. So, what else is there? Well, here's the next one. An experiment working alongside Max Planck took basically metal foil, and he fired light at it. And if you used a red bulb, I should probably make a red bulb red, huh? Use a red bulb, light would strike the aluminum foil, or the metal gold foil, or the iron foil, whatever would happen. Nothing but boring would happen. Nothing wrong with that. That makes perfect sense. No reason why light should mess up foil. He'd take a purple light, and the electrons would come flying out of it, like there's no tomorrow. Now, purple light's more energetic than red. Makes perfect sense. Except, what if the red is very, very bright? What if the purple is very, very not bright, dim? Well, then which one's putting out more energy? Is putting out more energy. So if the red's putting out more energy and the electrons are escaping the atoms because they have enough energy to escape, something's wrong. Why are the electrons here not getting the red? Why aren't they suddenly popping out in record proportions? It gets worse. Once they realize what's going on, they do another set of experiments which involve trying to make it so that you just receive one photon at a time. Okay? One photon at a time, the purple light ejects one electron per photon. The red light ejects nothing. No matter how many million photons you get in there, never going to get an electron out. So, for reasons that seem completely perplexing, some reason electrons can't store energy. This goes to the idea we were talking about before, where you have these nice, pretty shells. If an electron does not receive the exact amount of energy to get to here, or enough to get all the way out, it doesn't accept the energy because it's got nowhere to go. It can't just pick a random place and make its own shell. You could do that with a spacecraft. You can make a spacecraft go from a nice orbit and everywhere in between. You can park it anywhere you want to. Why is it electrons refuse this behavior? Because if they didn't, an electron receiving energy would pop out to its own shell, then pop out to another one, pop out another one. Eventually, the red light would kick it all the way out because it'd be free to go. It'd have enough energy to escape. Instead, it stores nothing. It says, if this photon's not good for me, I'm accepting it not at all. And in fact, if you pick a specific color that this thing's emitting for an electron when it drops down, if you pick a specific shade of red, you can actually make the electrons bounce out of only that specific color. A little bit more high frequency, a little bit less high frequency, it won't go to the next shell.